This is all work that's been funded by the Air Force here at Rice University. We're starting with the reductive splitting of carbon nanotubes to convert them into graphene nanoribbons. So if you take a carbon nanotube and you were to alkylate it, you would convert sp2 carbons to sp3 carbons and you'd lose the conductivity. And so what we've done is we've taken these and we've blended these into composites, and they're RF transparent, yet they're conductive, so we can do resistive heating. And we've been able to de-ice films. Live in a colder environment, you have to de-ice the window on your car. What you have to do is you have to wait for the blower to get hot to de-ice the front window. You can rapidly de-ice the back window because you have these little wires in the back where you do the resistive heating. But in this case, since they're transparent, you could do the same thing on the front window as well. And these are just these GNR films which are both RF transparent and optically transparent, yet we can do the dual heating. Here's an SEM of a composite film. You can see these graphene nanoribbons jutting out, which give a tortuous pathway if gas were to go through. Say industries like the oil industry, where they have explosive decompression problems, where what happens is you put a seal under high pressure, that seal will start to accumulate gas, and then when the pressure is released, that seal will blow as the gas is trying to escape from the seal. That's explosive decompression, and here we can keep the gas from getting in there in the first place. You can see that we get 70% higher current than platinum gives at a lower overpotential. We've been able to extend this to the use in supercapacitors. It shows you how when we water etch, you can see that we can double the capacitance just by doing this water etch, where we have hit the theoretical maximum of lithium. You cannot make a lithium-ion battery with a higher capacity than this. The typical graphite battery in your cell phone, in your computer, is tenfold less in capacity to this. We are running 100 times faster than the typical charge rate of graphite. A typical conventional battery would give them 300 miles distance in the Tesla Model S electric vehicle. With this battery, it would give them 1,150 miles distance. Here's another example of what we've been able to do with a carbon material. We can convert any carbon source into graphene at 1,000 degrees on nickel or copper. We've done it with roach legs, we've done it with Girl Scout cookies, we've done it with dog feces. Any carbon source will go to graphene. We've made something that we call LIG, or laser-induced graphene 3D foam. Then when we write on polyimide, what happens is it converts it to graphene in the air at room temperature. People who have had retinal degeneration, new artificial retinas that are coming out on the market, they're only 16 bits. They're powered by a pack on the belt, and then there's a wire that comes up. The wire goes underneath the skin, and then by RF, that artificial retina is powered, and you can see what looks like shadows. We've been able to show this so far by using mouse retinas that are placed on an instrument in the medical center. We don't need external power. We're using the photon itself, just like with the human eye. Go ahead and contact me. My website is listed there, and you can get my email from there, and I'm glad to answer any questions. Thank you.